Let us proceed. Welcome. Now, so yesterday we looked at the RSA signature, digital signature, and how, how to come up with one. And just before that, we had looked at the RSA algorithm itself, and we were trying to see how we can attack the RSA system. We had looked at integer factorization. We were seeing that the easiest way to attack it, although there are various ways of attacking the RSA, but we were trying to see how to attack using the integer factorization. And there are various algorithms of factorizing integers. And we had looked at the Pollard's row algorithm. We are supposed to look at the Pollard's P-1 algorithm. And then look at this one, which is applied in elliptic curves. So we shall again look at it, but after the elliptic curve, in studying the elliptic curves, we shall now look at this method of factorizing integers. Then there is also this quadratic sieve factorization. There is one that I had not included here, but it is the one I'm going to look at. The one we use perfect squares. So it's the one I'm going to look at today. If I look at the Pollard's P-1 algorithm. So I have called it utilizing difference of squares in factorization. So this is another way we can factorize a big integer given to us. And of course, it's, as we always say, the RSA is secure if the prime numbers are large enough, although there are algorithms in present to try and factorize that large number. Now, so this method of utilizing difference of squares will use this identity that is well known to us. This is how to factorize a perfect square. So it's a method I'm going to teach today. This one, we know it from high school, that if you're given x squared minus y squared, this can always be factorized as x plus y multiplied by x minus y. So this is the method I'm going to use to factorize integers today. So that means I've said to factor a number n, what we'll be doing is we'll be finding an integer b such that n plus b squared becomes a perfect square. You know what a perfect square is? We say that as a number is a perfect square if we can obtain its square root. For instance, you can say 1 is a perfect square because its square root, it can be written as 1 square. So its square root, okay, 1 is a perfect square because its square root can be obtained as plus or minus 1. Another 4 is also a perfect square because we know its square root. The square root of 4 to plus or minus 2. So that's what I mean by perfect square. In other words, 3 is not a perfect square because its square root is not a whole number. The square root of 3 is not a whole number. But 9 is a perfect square because the square root of 9 is a whole number. It's plus or minus 3. So that's what I mean by perfect square. Now, so what we'll be doing therefore, and it's what I've already stated, that if we are given a number n, we'll be looking for another number b, which when you take n and add this b square, what you get is a perfect square. So that's what we'll be doing. Some minutes, I'm trying to admit. It's okay. Now, so let's say just to go to example, but I think you've gotten what I'm saying. What I've said here is, I've said to factor number n, what we'll be doing is we'll be looking for a number b, such that n plus b square is a perfect square. In other words, we mean we'll be looking for a number b such that b, a plus b square gives us a square. So when you take b square this other side, what you get is n is a square minus b square, and this can be factorized to give us m plus b, a minus b. So you can factorize n to give us. So that is what we'll be doing. We just look for a number which, when we square it and add it to n, we get a perfect square. So I think I should demonstrate this by use of an example so that the point is clear to us. I want to begin by getting factorizing 713. 713. So as I've said, what we need to do is to determine a number b such that 7 plus b square is perfect square. So that one we do it by trial because we don't have that b. We're just trying. We're trying to see which one will give us a perfect. So we try one. We have this 713. So we add one square. One, if you add that, you get 714. 714 is not a perfect square because it will not give us a whole number, a square root whole number. Let's try 2. So this 713 plus this is 4. So 717. Again, this is not a perfect square. Then you try 3. 713 plus this is 9 will give us 722, which again, it is square root is not a whole number. Now you try 4. This is 713 plus 4 square, which is 16. This will be 729. But 729, the square root of 729 is a whole number because the square root of 729 is plus or minus 27. So then I just pick, whichever you pick, there's no problem because we'll be squaring. When you square, what you get is a whole number. Now, so what does that mean? What that means, let me just write at the bottom here so that you see what I did. But you can see we've found the b that we were looking for. Our b is 4. Our b is 4. So then what happens? What we have from this step, what we have is 713 plus 4 square is 27 square. So now take 4 square, the other side of the equal sign. You have 713, which is 27 square, minus 4 square. And we know how to factorize this, the right-hand side. The right-hand side is the same as 27 plus 4, 27 minus 4. These are right-hand side. You can factorize that way. So the first bracket gives us 31, and the second bracket gives us 23. So we found the factors of this number. We found the factors. So that means 713 is the same as 31 times 23. So we factored that number. So it's very easy factoring. So if you have a program, maybe you're then saying it's 713 plus I, and maybe you're defining your I, you see, it's I square, where I, you're defining I, and I is just 1, 2, 3, and so on, until you obtain a perfect square. Until you obtain a perfect, so when you obtain a perfect square, it's supposed to give you the square root squared. So the square root of this sum, then the square root of this sum is 27. Then from there you proceed. Okay, let's look at another example. I want to factor 493. Again, I'm looking for B, so that 493 plus B square will be perfect square. I don't know what B is, so I use trial. I try 1. 493 plus 1 square will be 494. I try using my calculator, and this is not a perfect square. Using a calculator, it will not give you a whole number. Square root will not be a whole number. The square root of 494 will not be a whole number. That's what I mean, not a perfect square. What about 2? 2 square will be 4, plus that, I get 497. What about 3? That would be 9, plus that, I have 542. Again, I test the square root. The square root is not perfect. It's not a perfect, it tells me that it's not a perfect square. Since it's not a perfect square, I proceed and try the next one. I get 549, which is not a perfect square. I try 5 square, which is 25, plus this gives me 518. This again is not a perfect square. So you're just using a square root to your calculator to find out whether it is a perfect square or not. And then you try this 6. 6 square will be 36. Added to this is 529. On using a calculator, 529, the square root, is plus or minus 23. But let's square it. When you square it, you get a positive number. So what we then have from this step, what we have is that 493 plus 6 square has given us 23 square. So you can take 6 square the other side of the equal sign, and you have 493, which is the same as 23 square minus 6 square. And when you factorize this using our knowledge from high school, this will be 23 plus 6 multiplied by 23 minus 6, where the first bracket gives us 29 and the second bracket gives us 17. So in other words, the number we wanted to factor has been factored. Wanted to factor 493, and if found, in fact, it's just times 29. It is 29 times 17. Now, so if 29 and 17 are prime numbers, then you are done. If they're not prime numbers, you can still try and see whether you can factor each one of them. But for this case, these two are prime numbers, because we are saying you want to try and attack the RSA, and the RSA, we know that as P and Q, which are prime numbers. And you know that M, for the RSA, M is public. So once you get what M is, once you get what M is public. So you have M, you only want to get P and Q. Once you have P and Q, you can find phi of m, which is then now p minus 1 multiplied by q minus 1. And once you have phi of m, and remember the other public thing was E, you can find the inverse of E, which is D, the decrypting key. And remember again, the ciphertext is, you can have access to it. Once you get the ciphertext, then you can decrypt using this D. Now, again, I want to just look at other examples so that we move slowly and slowly towards the bigger numbers, proceed the bigger numbers. So you can see we're now moving to bigger numbers. Just want to show that this method will still work. And when you use an algorithm, this method is fast also, is faster. Because remember, the other method that you will have used will have been to try all the prime numbers up to the square root of this number. Try all prime numbers up to the square root of this number to find out which one divides this. And those are so many prime numbers. Because what is the square root of this number? Let me just find out. The square root of this number is what? The square root of 2711 is 141. The square root is approximately 141. And so it's very numbers. You're trying. See this one. Like one of such that number one is M and it ciphertext is my internet. You can hear me, sir. Can okay. So 171,111 number.
I think we've lost Molimo. Let's just give him
Can
a
you hear me
minute.
now? My
He's
internet,
back. We had lost you, sir, for a minute. I think your connection is unstable. But we can hear you now. Yes, we can see your screen as well.
Yes, you cannot hear me.
You're breaking off, but we can hear you.
Yeah, my internet is stable, but I think is it now okay?
You're still breaking off, although we can see your screen and we can hear you, but you're breaking off.
Okay. Now, so what I was saying is that you see the whole essence of this
Okay.
trying to factorize numbers. Yes, Wanjiru?
No, it's okay. We can continue. We are good. We can hear you.
Thank you, thank you. So I was saying the whole essence of trying to see if we can factorize these numbers, one is that to see whether we can break, to know the security, just to know the security of the RSA. And of course, you know that the security of the RSA depends on the difficulty of factorizing integers. And we also have the security of the discrete log, which again we'll be looking at, which also depends on the difficulty of this factorization. And again, so that means it's very important for us to know to factor these numbers. We shall see how discrete log becomes very difficult. And we have crypto systems which depend on the difficulty of that discrete log. And even the elliptic curve also depends on that difficulty of the discrete log. And so it's good for us to know how to factor, therefore. So we began with the RSA, and we are seeing how we can break or attack that. Is because we know that M for the RSA is public. We know that M is public, and we also know that the attacker has access to the ciphertext. And so what this attacker requires to get from this M is just P and Q. And once he gets this P and Q, this attacker gets the product. And once he gets not the product, he gets the Euler phi, of M, which now is P minus 1 multiplied by Q minus 1. Remember that it's not easy to get Euler phi from M intact the way it is, because it's a very huge number. And for you to get it, you must factorize it first. You can't get it intact the way it is. So you must factorize, and factorize, get P, get Q, then get Euler phi. And you see Euler phi of M is very important because this Euler phi together with E are the ones which will help us to get the decrypting key, which is of course the inverse of E mod Euler phi of M. So that is why Euler phi of M is very important. And for us to get it, we must get P and Q, and then use it to get the decrypting key. Once you have this decrypting key and you have the ciphertext, you can always take the ciphertext raised to D mod M. And this is the plain text. So that is why we want to learn how to factor. And of course, there are so many algorithms. And so I'll take you through all of them. In fact, I've also said we shall look at the ones that are used in the elliptic curve. There's only one that I'll be looking at. And we have so many which are faster. We see now what varies is the speed. And the speed also depends on the the magnitude of the number in question. Now, so I wanted to factorize this number. Supposing it was our m, we just take 1 square, add it to it. This is what we get. Try and see whether its square root is there. We'll find that the square root is not a whole number, which means it's not a perfect square. So we proceed until we get a square root that is a whole number. So add 2 square, this is what we get. It's not a whole perfect square. Add 3 square, this is what we get. It's not a perfect square. Add 4 square, this is what we get. It's not a perfect square. Then add 5, get 144 as the square root. So then from this step, what do? What we have on the right-hand side is 2711 plus 5 square. And this is 144 square. So just take 5 square the other side of the equal sign. You have 2711 is 144 square minus 5 square. The right-hand side can be factorized as 144 plus 5 multiplied by 144 minus 5. The first bracket is 149, and the second bracket is 139. So that means the number we found as m has now been fully factorized. That is 2711 is the same as 149 times 139. So you can see it's very easy to factorize these numbers. It's very easy. I want to look at this example, and then we'll go to very huge. I show you how to find if they were very huge. Because if they were very huge, you want to minimize on the number of steps. Want to minimize the number of steps. Again, let's just do this. Want to find b square. So again, using our trial, we'll add 1 square, you get this, which is not a perfect square. Add 2 square, get that, which is not a perfect square. Add 3 square, you get this, is not a perfect square. Then again, proceed until when you add 6 square, this is what you get, and its square root is a whole number. So this is a perfect square. It means you stop. You stop there. Once you stop there, you now come and find your factors. 1189 plus 6 square has given us that 5 square. What about when we take 6 square the other side of the equal sign? That 5 square minus 6 square. And this is just that 5 plus 6 when you factorize. Multiplied by 35 minus 6. The first bracket is 41. And the second bracket is 29. So it means that these two are the factors of the number that we were factorizing. 41 and 39. Now, what about it if it was a very huge number? I've said here that it's rare that n plus b square would become a perfect square if you were to choose a random b, and if n is very large. If n is very large, it's rare that we can get this b, so that this sum becomes perfect square. So what do? I've said to work around this, what we normally do, we take this n and multiply it by another constant, multiplied by a constant, so that we have kn. And then write kn in this form. So you see what we'll be doing once you multiply, you see it was a huge number. So it's a huge number multiplied by this to get a very huge number now. Now, I think I should have refreshed the statement here, but I've said it's rare. What I meant is the steps will be many. The steps will be many, or it will take long. So when you multiply by a bigger number, the steps reduce. And I'll show you by examples. The steps reduce. And then this huge number, now write it as n square minus b square and factorize the same way we've been doing. After that, you've obtained A and you've obtained B. No, not A and B. You have the result from this bracket and the result from this other bracket. So this result from the first bracket combined with A, find the GCD. And also find this GCD. So these are the values from this. A minus B is this value. And A plus B is this value. So combine with A and get the GCD. The GCD that you get, supposing the GCD here is G, and the GCD here is H, supposing that is what you get. Then now, G and H becomes the factors of the number you are factorizing. Those becomes the factors. I've just said the essence of multiplying this number with another constant is to ensure that you reduce on the number of steps. Otherwise, without multiplying that, the steps become more. And in fact, if you try the examples we've just done and multiply those numbers by constants, you'll find that the steps may reduce in some cases. In other cases, will remain the same. But it's not easy for them to be more steps. Let's just try this number. Let's try this number. I want to factorize 22,881. I want to assume this is a large number. So if it's a large number, I multiply by a constant. I've chosen 3. So I want to multiply 3 by this number. I'm calling it n. So multiply by 3 and then add b square until we find a perfect square. So I've just taken 3, multiplied by it, then added 1 square. This is what I get. When I try to find the square root of this number, I find that it exists. In fact, I've done this in one step. Because the square root already exists. This number is a perfect square, so its square root already exists. It's 262. So now, from this step, what do I have? The left-hand side, I have this plus 1 square is equals to the right-hand side. So I've just taken 1 square, the other side of the equal sign. Let me write it what it was. It was 3 multiplied by 22881 plus 1 square is 262 square. So what I did, I took 1 square the other side of the equal sign to obtain this. And this can be factorized as 262 plus 1 multiplied by 262 minus 1. The first bracket here is 263. And this other bracket is 261. Now, so those are not our factors. We've said to get factors, we go further and now get the GCD of the number combined with what we've just obtained. So now, the GCD of the number we're factoring combined with the first number here. When you do it using the Euclid's algorithm, you find 263. And then now the GCD of this number and the other number is 87. So these GCDs are now the factors of this number. So what that means is that this number has the factors this and that. So that means it can be written as that. I claim that multiplying 3 by n reduced to the steps. Reduced to the steps. Let us see what it would have been were it that we had not multiplied. Let's see how many steps we would have used. Let's just try here. Just want to try somewhere here and see. Just open your calculator so that we move together. Just want to see whether it has reduced the steps or not. But I claim that it reduces the steps. My calculator, yes. So what I want to work without 3. I want to see. I want to take 22, just as we were doing earlier, 881 plus 1 square, and see whether I get a perfect square. So let me just open my calculator. I have 22, 881 plus 1 square. And this is not a perfect square. It's not a perfect square. What about plus 2 square? Plus 2 square. Again, if I were to take 22881 plus 2 square, again is not a perfect square. Let me take by plus 3 square. I hope you're using a calculator also. And you discover again that this again is not a perfect square, not a perfect square. What about plus 4? Again, it's not. Plus 4 is not a perfect square. What about plus 5 square? Again, it's not. I'm just using my calculator. What about plus 6 square? It's not a perfect square. So you can see we've already reached 6 steps. What about plus 7 square? It's not a perfect square. Just using my calculator. What about plus 8? It's not a perfect square because it's giving me 151.5. About plus 9 square. It's not a perfect square. What about plus 10 square? It's not. So we've already reached plus 10 square and we've not found a perfect square. So I claim multiplying this number by this constant reduced our steps. We were able to only use 1 step and then do the necessary arithmetic. So what I'm saying is, in some cases, multiplying these numbers by constants will reduce our working. Will reduce our working. So that is how you can modify your algorithm to see that now it performs very fast. You can see how this one will have performed very fast as compared to just using n plus I square. So when you now take n and multiply by k plus 1 plus I square plus I square, it reduces the steps and therefore your algorithm will work very fast. Want to look at another example? Now, somebody will have asked, is it possible to use 2? I've not used 2. I've not used 2. I've used 3. I'll explain that at the end of these examples. Why I have not chosen 2, but I've chosen on 3. Now let's try this. Again, we want to reduce the steps. We know that, of course, the steps can be more, but we can reduce by a constant. I choose my constant 3 again. And I want to multiply 3 by the number we were given and add. So the number we are given, this is an M, the N we found from the public domain. People are trying to converse, and we got this N. Want to factorize and get the P and Q. So I want to reduce the steps. I multiply it by 3. To the result, I add 1 square. This gives me that. And this is not a perfect square. I multiply 3 by the same number and add 2 square and see what I get. I get this again, is not a perfect square. I continue until I get a perfect square. I add 3 square to it. This is what I get. And again, this is not a perfect square. I continue. Add 4 square. This is what I get. It's not a perfect square. I'm just using my square root calculator to see whether I can get a whole number. Add 5 square. This is what I get. And this again is not a perfect square. Add 6 square. This is what I get. And again, this is not a perfect square. When I add 7 square, this is what I get. And my square root calculator gives me this. Gives me that the square root of this is plus or minus 104. And I know that I've reduced the steps. Otherwise, there would have been many. Otherwise, there would have been many.
I have a question.
Now, so, yes.
Can you repeat again? Where is that 3 coming from? Why 3?
Yes. I said I'll respond to that after the examples. I'll explain why not 2, why 3. But the question, the thing is, you know, supposing I have P, is that okay? And P is one of the factors of N. Supposing I have P, and I subtract 1 from it, for instance. Subtract 1 from it. And then multiply this result. You see, this is a prime number. This is a prime number. It's odd. It's odd. This prime number is odd because the only prime number that is even is 2. And so long as this number is bigger than 2 as prime number, it is odd. So when I subtract 1 from it, what I get is even. When you take an odd number and subtract 1 from it, what you get is even. Now, so I have this P and I've subtracted 1 from it, and then I multiply this result by 2, for instance. Just looking at this step here. Just looking at this step, this first step. Multiply this result by 2. When you multiply this result by 2, whatever you get here is not a perfect square. Not a perfect square. Now, even if this one changes to 2, instead of 1, if this is 2, you subtract again and do it. Let's do it mod something. You're doing it mod something. Again, this will not be a perfect square. But if I use 3 or any other odd number, I expect that whatever I get here will be a perfect square at some point. But if it's just 2 that I've used, if I would have used 2, I will not have reached a point where I can get a perfect square. I will not have reached a point where I get a perfect square. But 3 has given us that thing, has given us a perfect. So I think I can even use 5 or 7 or any other odd number, and I'll get a perfect square, but an even number will not give me, because I'm taking an even number. Let me see. We can take examples. Let me see if we can get an example, a good example. I cannot think of the best example, but what I'm just saying is, if I was to multiply by 2 on this side, and then do whatever I've done, but 2 on the other side, I will not have reached a point where I get a perfect square. And the reason is just what I've given here. For instance, you have P, let me assume P is 7. I subtract 1 from it, for instance, at this point. If I subtract 1 from it, this will give me an even number, which is 6. So when I multiply this 6 by 2, I get number 12, which is not a perfect square. If I proceed again that way, even subtract another number from it, just like that, I multiply by 2, at every point, there's no point you'll reach a perfect square. I don't know whether the explanation is, you understood it. But the thing is, it's good to use this 3 or any other number that is not even, for you to be able to get a perfect square at some point. Because you can see, it's not that every time we are getting a perfect square. It's not every time. But when we are using these other odd numbers, we are sure that at some point we will come across a perfect square at some point. But when you're using an even number, that assurance is not there. That assurance is not there. Okay, so we had reached here. That is 104. So from this point, this is what we have on the left side. The left side, we have 3. What is it? We have 3 multiplied by, the left side, we have 3 multiplied by 35, 89. Then we are adding there. Let me just a minute. Okay. Yes, so the left side is plus 7 square. And then the right side is 104 square. Just take 7 square, the other side with the equal sign. What you get is 3 multiplied by 35, 89, equals to 104 square minus 7 square. And this part, the right side can be factorized. It will be 104 plus 7 multiplied by 104 minus 7. So when you add 104 plus 7, what you get is 111. And when you subtract 7 from 104, what you get is 97. And again, these are not the factors. Because we had multiplied this number by a constant, so we then have to get the GCD of what we've just obtained combined with the n. So our n is that 589, and one of the numbers is 11. This GCD gives us that 7. And the next, we have the number 97, and n is that, the GCD is 97. So these two now become the factors of the number n. Those two becomes the factors. Again, I want to take another attempt on a bigger number, another attempt. And I want to claim that doing this reduces the number of steps. So at your own time, try and do the same question without multiplying by constant and see how many steps you can do. In some cases, it will take even 50 steps in some cases. Now, let's try 1 square, and that gives us this. Just confirm. I think it gives us that. But the issue is that it's not, whatever you get here is not a perfect square. I don't know whether, let me just try it. Just do it again. The answers I've written there, just confirm them. Confirm the first one. 3 multiplied by 24459 plus 1 is, oh, yeah, I didn't check. These numbers are not correct. Only 1 is correct, this one. This one is supposed to be 73, 378, which is not a perfect square. Yes, what about if it's 2? If it's 2, this would be 73, 381. Again, is not a perfect square. You see, because of typing, I just copied the first near and pasted here, and then it changed a few things. Then this is the one I wrote. The other ones I forgot to change. When it's 3, that becomes 73, 386. But again, it's not a perfect square when you try to find the square root. Then 4, that would be 73, 393. And again, that would be not a perfect square. About 5, this would be 73, 4, 2, which is not perfect square. And then 6, this would be 73, 413, which is again not perfect. And then what about 7? This would be 73, 426, which is not perfect. So let me just try the last one. It's 8. That is correct. 73, 441. Let me see whether the square root is perfect. The square root of 73, 441 is 271. That's correct. So those are the only changes there. So that means this part is equal to this part. In other words, I'm saying 3 multiplied by 24, 459, plus 1 square, the same as 271 square. When you take this, not plus 1 square, it's plus 8. Plus 8 square gives us 271. When you take 8 square the other side of the equal sign, what you have is 3 multiplied by 244, 59, 59 is equals to 271 square minus 8 square. And this right-hand side can be factored to be 271 plus 8, 271 minus 8. The first bracket is 279. And the second bracket is 263. So this gives us this product. And they are not the roots. So to get the roots, no, to get the factors, we have to get the GCD of the number we're looking for, which was 24, 459, combined with the 279, and also find the GCD of the same number combined with the 263. The first GCD is 79, and this other GCD is 263. So in other words, we factored this number. Is it 73? No, this is 93, not 79. Where am I getting 79 from? It's supposed to be, this GCD is supposed to be 93. 93. And this other GCD is 263. You can see that 93 here is not a prime number. You can see be factored to be 3 times 31. That means the complete factorization of the number, therefore, is 3 times 31 times is the complete factorization of that number. That is the complete factorization of this number. So that is what I've written here. And so that is how I want to look at that. That is how to do that. But I had, okay. There's something I'd written here just for security reasons. I had said, although it concerns the Pollard's algorithm, but it still applies to both. What I've said is, if you have
Yeah, I think we can't hear the teacher.
Yeah, because of some network. You can now hear me?
Yes, we can now hear you after you stop sharing.
Okay, thank you. So let me just now share. There was a problem with the internet, so I was disconnected. Now, so what I was saying is, supposing you want to create your RSA algorithm, how do you choose your numbers? You see these numbers here, it's you choosing the P, you're choosing the Q. The best way to choose your P is to choose P such that P minus 1 does not have very many small prime factors. I was just giving an example. Supposing your P is 7, what is P minus 1? P minus 1 is 6. This is the factorization of 6. It has only smaller factors. What if, supposing you chose a number like your P, let me just see what it is. Let me say like 47. I don't know whether 47 is a prime number. Is there a number that can factor that? 47? I think it's a prime number. This is a prime number. So I think for 47 will be a good example. I just want to use it as an example to show how you are choosing your P and Q. What is P minus 1? What is P minus 1? Supposing this is my P. What is P minus 1? P minus 1 is 26 or 46. What are the factors of this number? 2 goes here 23 times. So you can see I have 2 and then 23. There are no other small prime factors. I don't have 3, I don't have 7, I don't have 11, I have 23. And remember that we say that your P should be a very huge number. So what I'm saying is that if P is a very huge number, 2 will always be a factor of that P minus 1. But after 2, try and avoid so many small prime factors. So that you have 2, and then from 2, you have another number which is almost, and I've said here, should be almost a half of P. The other factor should be almost a half of P. So that if your P is, for instance, 263, I don't know if that is a prime number, but I'm just using an example. Supposing this is a prime number, and 2 is a factor of this number, then almost a half of this what is 2 minus okay, P minus 1 will be 262. A half of this number should be factors which are almost a half of P. Factors which are almost a half of, or even larger. That will enable to factorize algorithms, because these algorithms are very fast, that have smaller. As I said, this has a security. The internet is, my internet is very unstable. But that is a point I was trying to make, that as you choose P for your RSA and also Q, of course, you're choosing the two prime numbers. Ensure that they do not have as a smaller prime factors. They should have only two, and maybe from there go to another very huge prime factor. That is a point I wanted to emphasize as we end. And I don't know that there's something else. No, it's nothing else. That is the only thing I wanted to emphasize. Okay, thank you.
See you tomorrow. Thank you for your time.